Hi everyone. In this tutorial, we are going to look at covalent and ionic bonds. We are going to look at their physical properties while also drawing Lewis structures to see the bond interaction. First, we are going to look at some background information on the discovery of the bonds. So, who discovered covalent and ionic bonds? Gilbert and Lewis discovered covalent and ionic bonding in 1916. He proposed that ionic bonds involve the transfer of electrons, while covalent bonds involve the sharing of electrons. This discovery satisfies his octet rule, which is that compounds need to achieve a full outer shell, which is 8 electrons, by either transferring or sharing electrons. First, we are going to look at ionic bonds. So ionic bonds happen when there is a transfer of electrons between a metal and a nonmetal. We can also determine ionic bonds by their electronegativity difference, which is anything greater than 2.0. This makes all ionic bonds polar. Ionic bonds involve cations and anions. A cation is a metal that loses an electron, which creates a positively charged cation, and an anion is a nonmetal that gains an electron, which creates a negatively charged anion. So the compound with the least amount of electrons is in its outer shell, and it transfers its electrons to the other compound to create a full outer shell. When naming ionic compounds, we start with the cation first, then the anion, and add an IDE ending. Some real-world examples of ionic bonds are NaCl, which is sodium chloride, and just regular ordinary table salts, or sodium hydrogen carbonate, or sodium bicarbonate, which is just regular baking soda. So now let's look at how we draw a few ionic compounds. So first up, we have sodium fluoride, and we know it's ionic because sodium is a metal and fluoride is a nonmetal. So you can see here that sodium has one valence electron and fluorine is in need of a valence electron. So sodium is going to transfer that electron over to fluorine and cause the charges to become a negative charge and a positive charge. Next up, we have calcium chloride. Calcium is the metal and chlorine is the nonmetal. So you can see here that calcium has 2 valence electrons and both of the chlorines are in need of 1. So calcium is going to transfer those electrons over to the chlorine, and that is going to satisfy the octet rule and give us our full outer shell. And lastly, we have beryllium oxide, beryllium being the metal and oxygen being the nonmetal. Beryllium has 2 valence electrons, oxygen is in need of 2, so beryllium transfers over both of those electrons and it creates the full outer shell. Next up, we're looking at covalent compounds. So covalent compounds are when there's a sharing of electrons between nonmetals. Both compounds are in need of the same number of electrons to achieve a full outer shell, resulting in the sharing of electrons to satisfy the octet rule. They allow molecules to share electrons with other molecules, which creates long chains of compounds and allows more complexity in life. Covalent bonds form single, double, and triple bonds, and they are interactions within the sigma and pi orbitals. Most acids are considered covalent, although there are some cases where acids are not covalent, but it is not as common. So to name these bonds, we start by naming the element closest to the left side of the periodic table, then the next element with an IDE ending. There's also the use of prefixes when naming these compounds. Here is a list of them. So we have mono, di, tri, tetra, penta, and you'll see in our examples when we get to use these. And some real-world examples of covalent bonds are carbon dioxide, which is just used in fluids, and dinitrogen monoxide, which is just regular water, or H2O. So how do we draw covalent compounds? First up, we have methane, and both of these compounds are nonmetals. That's how we know it is covalent. So carbon has 4 valence electrons and hydrogen has 1. So when we calculate the number of valence electrons we have to work with, we have 8. So when we put these together and draw them as a Lewis structure, we see that hydrogen is going to share its 1 valence electron with the carbon to create a full outer shell for both hydrogen and carbon. Next up, we have dinitrogen tetroxide, and these are both nonmetals. So we have 34 valence electrons to work with, and if we were to count all of these dots, it would be 34. So you can see between the nitrogen and the oxygen, we have a double bond here. That is because the oxygen on the top is sharing its electrons with the nitrogen, which creates a double bond. So that gives us a full outer shell for every compound. Every element has 8 electrons in its valence shell. And lastly, we have hydrochloric acid. Both are nonmetals, 8 valence electrons to work with, and hydrogen is going to share its electrons with chlorine. This creates a single bond and satisfies our octet rule. Now we are going to look at some physical properties of ionic and covalent bonds. So ionic bonds are crystals, and this is because of how positive and negative charges line up within the bonds. They can only be solid at room temperature, and they do not conduct electricity when they are in this solid form. But when they're dissolved in water, an electrically conductive solution is formed. These are what we call electrolytes. So when you put them in water, the ions separate and become free-moving ions, and this allows electricity to be conducted in the liquid. Ionic bonds have high boiling and melting points because they're always a solid. They are also very hard and brittle, so they shatter easily with force, and they can't be bent or deformed. Covalent, on the other hand, can be a solid, liquid, or gas at room temperature. They are poor conductors, and they don't dissolve in water, which means they don't have any electrolytes. Covalent bonds have lower boiling and melting points compared to ionic ones, and covalent compounds are very flammable. Now we are going to review the electronegativity rules. So if you look here at my chart, we can see that anything less than 0.5 is considered nonpolar covalent. Now this is when there is an equal sharing between the 2 atoms in the bond. One example would be carbon disulfide. Next, between 0.5 and 1.6, it is considered a polar covalent bond. This is when there is an unequal sharing between the 2 atoms in the bond, and one example would be ammonia. And as we mentioned before, our ionic bonds have an electronegativity difference greater than 2.0, and they involve the transfer of electrons. So we can see here between 1.6 and 2.0 that there's a little bit of a gray area, and there are 2 different examples here, or 2 different situations that can happen here. So if there's a metal involved, that makes it ionic. But if there's a non-metal involved, that makes it polar covalent, and we will see that in our next example with hydrogen fluoride. So now we're going to dive further into the classification of the hydrogen fluoride bond. It is described as polar covalent because of the difference in electronegativity and the fact that hydrogen and fluorine are both nonmetals. So hydrogen's electron negativity is 2.1 and fluorine's is 4.0. When you subtract these from each other, you get 1.9. Now, this is in the gray area of the electronegativity classification, and as mentioned before, if it only involves nonmetals, it is considered polar covalent. So, hydrogen fluoride has an imbalanced electron cloud because there's an uneven attraction between the hydrogen and the fluorine atom. To represent this, we draw this symbol here on the left-hand side by the H end to show that the molecule has a slightly positive charge with respect to the F end, and this negatively charged symbol here on the right-hand side to show that the molecule has a slightly negative charge with respect to the F end. Hydrogen fluoride is actually a compound that can melt glass, which is quite interesting. And the physical property is that it is a gas at room temperature. And when we were looking at our physical properties, we saw that covalent bonds are gases at room temperature, which is why it is considered also polar covalent. Now we are going to look at the following compounds and determine if they are ionic or covalent. So remember, ionic bonds contain metals and nonmetals, and covalent bonds contain nonmetals only. Up first, we have potassium phosphate. And if we look at this structure here on the left, we can see that there's covalent bonding between oxygen and phosphorus. But there's also ionic bonding between potassium and oxygen. So potassium is giving one of its valence electrons to the oxygens in need. So it's transferring them, which is considered ionic, and also potassium is a metal, and phosphorus and oxygen are nonmetals. So this is between a metal and a nonmetal. It is an ionic bond. Next up, we have carbonic acid. So you can see here that there's sharing between all of the elements, there's no transferring going on, and also hydrogen, carbon, and oxygen are all nonmetals, which means it is covalent. Next up, we have sulfur hexafluoride, and this is also, you can see that there's sharing going on between the sulfur and fluorine atoms. So this is also covalent, and sulfur and fluorine are also all nonmetals. Lastly, we have sodium carbonate, and you can see here that there is covalent bonding between carbon and oxygen. We have a double bond here, but our sodium atoms are also transferring their outer valence electrons to the oxygens to achieve the full outer shell. So since there's a transfer going on, and also that sodium is a metal, and the rest are all nonmetals, it is an ionic compound. I hope you guys learned something new in this tutorial about covalent ionic bonds. Thank you very much.